Welcome to The Explainer. Today, we're diving into a revolution in manufacturing, and I want you to forget everything you think you know about making things. You know, the clang of a hammer, the heat of a forge. We are stepping into the age of the digital blacksmith, where incredible new metals are forged not with fire and force, but with lasers and code, built one microscopic layer at a time.
So that brings us to a huge question. How do you build the impossible? How do you create things with shapes and strengths that, until now, have been pure science fiction? Well, the answer is in a technology that basically flips centuries of manufacturing on its head. It's called additive manufacturing.
All right, here's our roadmap for this explainer. We're going to start with the big idea, then we'll step inside this digital forge. After that, we'll uncover the secret recipe for making these super metals, check out the mind-blowing results, and finally, really understand why this changes pretty much everything. Okay, first things first. Let's get our heads around the big idea that makes all of this even possible. It's a totally new way to build. You see, for hundreds of years, making something meant starting with a big block of material and just carving away everything you didn't want. That's called subtractive manufacturing. Additive manufacturing, or AM, does the exact opposite. It builds things from the ground up, adding material layer by tiny layer, all guided by a digital file. This lets us create these incredibly complex shapes that were literally impossible to make before.
And listen, this isn't some sci-fi dream. It's already here. And it's totally transforming industries where you just can't compromise on precision and performance. We're talking about things like jet engine parts that are both lighter and stronger, or custom medical implants that are perfectly matched to a specific patient's body. AM is already a game changer.
So let's zoom in a little bit and see how this actually works with metals. We're about to step inside the digital forge and look at a process called Direct Metal Deposition. Direct Metal Deposition, DMD for short, is a really powerful type of AM. Basically, it uses a high-powered laser to create this tiny pool of molten metal. Then, it feeds either a stream of metal powder or a thin metal wire right into that pool. It instantly melts and fuses with the layer beneath it, building up a fully solid, super dense metal part one layer at a time.
Now, there are two main ways to feed metal into the forge, and they both have their trade-offs. You can use a powder feed, which is super versatile, but, it can be a little less efficient and sometimes leave a rougher surface. Or you can use a wire feed. That's way more efficient, much faster, but you might give up a little bit of that fine detail precision. It's all about choosing the right tool for the job. So, if DMD is the forge, then what we call the process parameters, well, that's the blacksmith's secret recipe. And every single ingredient, every little variable has a huge impact on what comes out at the end.
Think of it like you've got three main dials to turn. First, how powerful is the laser? Second, how fast is it moving across the surface? And third, how much metal are you feeding into the pool? Getting this recipe just right is absolutely critical. It's how you control the final part's strength, its hardness, its entire performance. And this quote right here, well, it really nails the core concept. We're not just controlling the outside shape of the part anymore. By carefully tuning these parameters, we are literally designing the internal architecture, the very grain structure of the metal itself as it's being born. So, how does changing the recipe actually change the metal itself? Well, it all comes down to what's happening at a microscopic level, in something we call the microstructure. Think about the grain in a piece of wood, right? A fine, dense grain makes for strong hardwood, but a wide, loose grain can be brittle. It's the exact same idea with metals, just on a scale you can't see. The size and shape of these tiny crystal grains make up the metal's microstructure, and that is what determines its strength. And with DMD, for the very first time, we can control that grain as it forms. Okay, to see just how powerful this is, let's look at a really cool experiment from the Source Research. Scientists were working with a common titanium alloy, and they decided to change just one super simple thing. Check this out. When they built the part continuously, no breaks, it had a tensile strength, which is just a measure of how much you can pull it before it breaks, of 880 megapascals. But then, they programmed a simple 2 to 3 minute pause between printing each layer. Just a little pause. And the strength jumped to 980 megapascals. That's an 11% increase in strength just from letting it cool down for a second. Incredible, right?
Okay, that was impressive, but what if we get even crazier with the recipe? What if, while we're building our titanium part, we start mixing in a fine ceramic powder called titanium carbide? And the results are just staggering. By mixing in just 15% of this ceramic, the material's strength went through the roof, jumping by nearly 20%. What's happening is these tiny ceramic particles are weaving themselves into the metal as it cools, acting like microscopic rebar, and creating a whole new thing, a metal matrix composite, that's fundamentally stronger than the original metal. So what does all this mean? Let's take a step back and really look at the big picture here, because the future this kind of control unlocks is pretty incredible. Here it is, the main takeaway. We have moved past simply manufacturing parts. We are now designing the very material a part is made from in real time as we build it. It's like being able to tell every single grain of metal exactly where it needs to go and what it needs to do. So all these findings give engineers this powerful new playbook. We now know which levers to pull and which dials to turn to fine-tune a material's inner structure. We know something as simple as a pause can make a huge difference. This opens the door to creating entirely new materials on demand, each one perfectly tailored for a specific job. This technology fundamentally changes our relationship with the physical world. It opens up a new frontier where the limits of what we can build are no longer defined by the materials we happen to have, but by the materials we can imagine. The age of the digital blacksmith is officially here, and the only real question left is, what will we forge next?